go ahead and do the FOIL method. We get our first terms, gives us x squared. Our outer term is -4 times x, and our inner term is -4 times x. So if we combine those, we get -8x. And our last is -4 times -4, just +16. So we just replace the x minus 4 squared with x squared minus 8x plus 16. That's the limit as x approaches 0. X squared minus 8x plus 16 minus 16 divided by -2x. Okay, well, the positive and -16 cancel each other out. That leaves us with the limit as x approaches 0 of x squared minus 8x divided by -2x. Okay. So from here, we can just factor out an x from both of the terms in the numerator. That x a little clearer. There we go. So we have the limit as x approaches 0. Factor out that x, that just gives us x times x minus 8 divided by -2x. Now, once it's factored out, we can go ahead and cancel this x with that one. So x divided by x is just 1. So that leaves us with a limit as x approaches 0 of x minus 8 divided by -2. Okay. Now, we couldn't do direct substitution up here because we had a denominator of 0. But we can do it here because we won't get an undefined value. So we're going to try our direct substitution. So if we plug it in, that just gives us 0 minus 8 divided by -2. Which is -8 divided by -2, which is just 4. Okay. Now the second method, I'm just going to kind of put it right here. It should all fit there. Where if we look at the limit of x minus 4 squared minus 16 divided by -2x as x approaches 0, we can see that the numerator is a difference of squares. And if you remember difference of squares, it just states that if you have a squared minus b squared, that's equal to, give that a little more room, Just know I'm going to run out of room there. And let me just kind of block that off. I'll put it underneath it. A squared minus B squared is equivalent to A plus B times A minus B. Okay, so we can get that entire numerator and factor it using difference of squares. So that gives us x minus 4 squared minus 4 squared. So that gives us a plus b. So that's x minus 4 plus 4 times x minus 4 minus 4. Remember, that's 16. We could rewrite that as 4 squared. Where your a is x minus 4 and your excuse me, and your b is 4. All divided by negative 2x. So that limit as x approaches 0, we simplify inside of each of those sets of parentheses. We have x minus 4 plus 4. Those two cancel out. So we have x times x minus 4 minus 4 is x minus 8 divided by negative 2x. Okay, so that brought us right to this, wrong one, right to this step. So we could see, we just cancel out the x's and do all those steps, and we end up with 4. So no need to rewrite the steps after that. But that was just to show that there's not always just one path to the answer. Sometimes you can go different routes depending on what you remember. All right, any questions on that one? All right, leave that up there for a few seconds. Let everyone finish writing. Yes.
This isn't a question. But, could I close the door? I find the lecture in the other room.
Oh, yep, go right ahead. All right, anyone still writing? All right. So now we're going to look at the squeeze theorem. Also known as the sandwich theorem. Okay, so what if we let f of x, g of x, and h of x represent 3 functions that are defined over a certain interval? defined over an open interval from x equals a to x equals b. Except possibly at c, where we know that c is an element of a and b. That just means that c is somewhere in that interval. So you see that symbol, it's like is an element of. So if you listed every value between a and b, c is in there somewhere. Make that a little clearer. It looks like it is on element of. There you go. Okay. So let's say in that interval, if we know that the function f of x is less than or equal to the function g of x, and the function g of x is less than or equal to the function of h of x. So basically, g of x is between f of x and h of x. For every value of x that is not equal to a and is not equal to b, and we know that the limit as x approaches c of f of x is equal to some value that we will call L. Okay, and the limit of h of x is equal to that same value. Okay. Now, if all of these conditions are met, then we can finally say that we know that the limit of g of x as x approaches c is also equal to that same limit value L. Move that up a little bit. Go. Okay. Now, visually, all this means is that if we take some x and y axis, bring that up a little bit. Okay, so let's say we take some function, put it right here, or this is our function h of x. on this function, let's say right at this point, we'll call just right here, that's just above some value c, where we know that value c is somewhere in the interval between some value a and some value b. Now, it could be negative if you want to make it negative, but just for the sake of this example, we're just making them both in the same quadrant. So let's say if you have another function, let's say this function just kind of goes here and it gets really close to that one in that same spot. Let me make that give that a little more room. And there we go. And that's our function f of x. Okay. So we see that both of these right at that point C, they approach this value here, and that's the value, the limit value that we will call L. Okay, so we know the limit of f of x as x approaches c is that value L, and the limit of h of x as x approaches c is that value L. Okay, so both from the left and from the right are getting closer and closer to that limit value. So what the squeeze theorem tells us is that if we have some other function where it can be anywhere outside of that interval, but inside of that interval, let's make that a little shorter so I can actually write what function that is. We'll say this is our function g of x. Where if the limit below it has a limit of this value L, and the function below it has a limit value of L, and the function above it has a limit value of L at x equals c, or x approaches c, then we can say that the limit of g of x as x approaches c is also that same value. Remember, we're just looking for this interval here. Now, outside of here, this could fly up past it, and we're not even worried about that, just between that a and b. All right, anyone still writing? Okay. All right, so let's say, for example, we wanted to, let's say if we have negative 2x squared minus 20x minus 50 is less than or equal to some function g of x, and it's less than or equal to 2x squared plus 20x plus 50 for the interval from -6 to -4. So we want to evaluate the limit of g of x as x approaches -5. Okay, so first thing you're going to do is you're going to find the limit of each component, 2 on the outside and the g of x in the middle. Or you can say each expression. So that gives us the limit as x approaches -5 of -2x squared minus 20x minus 50. Oops, I'm trying to write small to make sure I get everything on that line, but don't want it too congested. -2x squared minus 20x minus 50 is less than or equal to the limit of g of x as x approaches -5, which is less than or equal to the limit as x approaches -5 of 2x squared plus 20x plus 50. And then from there, you just apply direct substitution. So we plug in -5 here. That gives us -2 times -5 squared minus 20 times -5 minus 50 is less than or equal to the limit of g of x as x approaches -5. And that's less than or equal to, we apply direct substitution here, 2 times -5 squared plus 20 times -5 plus 50. Okay. So we have -5 squared, which is 25, times -2, which is -50. So -50 and -50 is -100. If you multiply these two, that gives you +100. So this just simplifies to 0. So we have 0 is less than or equal to the limit of g of x as x approaches -5. Less than or equal to, here we have -5 squared, which is 25 times 5 is 50. So if you add 50 to this 50, you get 100. And here you get -100. So this is also 0. Okay. So if the limit below g of x is 0 and the limit above g of x is 0, we know that by the squeeze theorem, the limit of g of x as x approaches -5 is also 0. Okay. Now, if you ended up with two different numbers and you're absolutely positive there's no error, then that really doesn't tell you anything. It doesn't tell you what the limit is. So if you had 0 here and 7 here, the limit of g of x could be any number between that. So really an infinite number of possible limits for that one. So this only works when your limit below and limit above the function, they're both the same. All right. Any questions on that one? All right. Anyone still writing? Oh, still writing. All right. Okay, so now we're going to look at special trig limits. Okay. Now, these are just ones that kind of stand out because they're a little bit different than the other ones we're going to see, where you just have basic sine, cosine, tangent, and all of those. Here, if you have the limit of sine of x over x, as x approaches 0, we know that's equal to 1. And we know that if you have the limit as x approaches 0 of 1 minus cosine of x divided by x, that's equal to 0. Now we're going to prove these later on, but for right now, we're going to be using them. Okay. So let's say, for example, you wanted to evaluate the limit sine of 8x divided by 8x as x approaches 0. Okay, just going to rewrite that. The limit as x approaches 0, sine of 8x divided by 8x. Now, as long as your angle and your denominator are the same, this is just going to equal 1. Our angle and denominator are the same. Now, if they're not the same, a lot of times it's a pretty quick fix. So what if we wanted to evaluate the limit as x approaches 0, sine of 3x divided by x? Well, we have the limit as x approaches 0, sine of 3x divided by x. We have to make our angle equal to our denominator. So all we have to do is multiply this by 3 over 3. That gives us the limit as x approaches 0. I'm going to put a little bit of space in front of this limit. So that's sine of 3x. And we can multiply these two. And that gives us 3x. And this 3 in the numerator, we can just go ahead and factor that out right to the front. Or you could factor it up there, but it's just easier to factor it out to the front. Okay, so we can see here, we know the limit of sine of 3x divided by 3x as x approaches 0, since our, not degree, our, I guess you could say degree, more of a unit of measure because it could be radians. Our unit of measure and our denominator are both the same. So that's just 3 times 1, which is just 3. Okay. So any questions on either one of those? All right. Okay. So sometimes they're nice and neat like this. Sometimes they're a little bit tricky. Oh, sorry, anyone still writing? All right, so they're a little bit tricky. You just have to kind of mess with it a little. So what if we wanted to evaluate the limit as x approaches 0 of 3 times tangent of x divided by negative 6x. Okay, so first thing we want to do is we want to get rid of that tangent. And we can do that because we know that tangent of x is equal to sine of x over cosine of x. So we can rewrite this as the limit as x approaches 0. At tangent x, we're just going to put that on the side. That's just 3 divided by negative 6x times tangent of x. Where we can go ahead and replace that tangent of x with sine over cosine. The limit as x approaches 0. And you could simplify that if you want to here. You could wait till the end. Doesn't matter. I'll say negative 3 over 6x times sine of x or cosine of x. Okay. So if you look at the denominator, you have 6 times x times cosine of x. Where they're all multiplied, we know that multiplication is commutative, which means we can shuffle those around. Same way if you have 3 times 4 times 5 is the same as 4 times 3 times 5. Doesn't matter what order it's in. So we can shift these two around. So that's the limit as x approaches 0. Negative 3 divided by 6 times cosine of x times sine of x over x. Okay. Still 6 times x times cosine of x, just kind of shuffled around. So if you remember your limit properties, you can distribute that limit to both of those factors. So we have the limit as x approaches 0 of -3 divided by 6 times cosine of x times the limit as x approaches 0 of sine of x over x. Okay. Now with both of these, you can use different methods for solving, because this one, you can just use direct substitution. And this one, by these special trig limits, we know that the limit of sine of x over x as x approaches 0 is just equal to 1. So if we use direct substitution, that gives us -3 divided by 6 times cosine of 0 times 1. Well, you know, cosine of 0 is just equal to 1. So that gives us -3 divided by 6 times 1. Times 1, we don't even have to write that down again. That's just -3 over 6, which simplifies to -1/2. Okay. And if you notice, I kind of bounced around that negative from the bottom to the front to the top. They're all the exact same thing. So if you have -3 over 6, that's the same as 3 over -6, and that's the same as -3 over 6. So it doesn't really matter where you put it. All right, any questions on that one? All right, anyone still writing? All right. Okay, so we're going to go ahead and start on section 2.4, which covers continuity. Okay, so we know just by definition that a function that we will call f could be f of x, f of t, excuse me, whatever the independent variable, we'll just say some function of f. Oops. Okay, we know it's continuous if all three of these conditions are met. The first condition is that f of c is defined for every c that is an element of your interval. That should look more like curve. There we go. Element of the interval. Okay. So if your interval is from -7 to +34, then c is just a value somewhere in there. So this is just kind of a broad way of saying that. So this class will just be full of brand new notations. Okay, the second condition is that the limit of f of x as x approaches c exists. And the third condition is that the limit of f of x as x approaches c has to equal f of c. Okay, so let's see how the graph would look if they failed any one of those conditions. Okay, so let's say if we have a graph on the xy axis, and on some interval from a to b, you have a function where it's undefined in that value that we will call c. And this is your function f of x. Okay, so we can see here this is not continuous since f of c is not defined. Okay, so what if we have another function? X and Y axis. We're on the interval from A to B. So if we have a function where it's a piecewise function where the left part of the point f of c, and it kind of breaks up and continues on the rest of the way. Okay. Well, if we look at this one, we know that as you approach c from the left, the limit is about right here. We'll say that's, I'll say L number 1, just to not use C, is equal to some limit value L number 1 from the left. If you approach C from the right, it has a different limit value. We'll call that limit number 2. Okay. So we know this is not continuous. Well, you can kind of look at it and tell it's not continuous. But by definition, it's not continuous because the limit of f of x as x approaches c doesn't exist, because the limit from the left and from the right are not the same. Not continuous since the limit of f of x as x approaches c from the left does not equal the limit of f of x as x approaches c from the right. That means just the limit of f of x as x approaches c is, well, it does not exist. And last, let's say if we have a function let's say if we have a function where it looks kind of like this one, where it's undefined at a certain value, at c, of course, in our interval from A to B. Okay, but say that value does exist. F of c does exist. So we can say f of c is equal to any number. We'll say some number L1, and this limit is some number L2. So just to avoid confusion, I'll say this is just f of c, just to keep it clear. Okay. So we can see that the limit exists. Because the limit as you approach c from the left is the same as the limit as you approach c from the right. So the limit exists, but we could see that the limit of f of x as x approaches c does not equal f of c. Okay. So if you plug in c, you'll get whatever value this is. But it's not equal to the limit as you approach it from the left and from the right. Okay. So if you want to visualize continuous functions, just think about a graph where you can roll your pencil down the whole thing and not have any holes or breaks or anything like that. Or if you have a hole here, you have to kind of jump over it and keep on going. Here, you can't roll your pencil all the way through. You'd have to pick it up and move it over here. Same thing here, you have to pick it up, keep it going. Continuous function would just look like this. No breaks, no holes, nothing. Or just like that. Any function at all where you don't have any of these problems. All right. Any questions on any of those? All right. Anyone still writing? Okay. Now we're going to look at the types of discontinuities. Clean that up a little. So discontinuity functions or discontinuous functions are just functions that are not continuous. Okay. So the first is a removable discontinuity. We kind of looked at that before. We were able to kind of manipulate the function to find the limit. Still wasn't defined at that value, but we were able to find the limit. Okay. I'll say the function can be made. Temporarily continuous at f of c. Okay, and that just means temporarily to find the limit. It doesn't change what the actual function is. Okay. You also have non-removable discontinuities. Okay. These will remain discontinuous no matter what. There's no way to manipulate that. With no limit. Now, this is also called the jump discontinuity. Okay. And you have your infinite discontinuity. It's basically your vertical asymptote. And that's just where your limit of f of x as x approaches c from the left is either positive or negative infinity. And the limit of f of x as x approaches c from the right is either positive or negative infinity. Okay, so let's say, for example, we have f of x is equal to 1 over x. Back up a little bit. So if we look at this graph, let's say if we look at it as x approaches 0. Well, if you plug in your positive values, the graph kind of looks like this, and it keeps getting closer and closer and closer to 0, but never actually touches x equals 0. Same thing on this side. It just gets closer and closer and closer without actually touching x equals 0. Okay, so there's no way we can manipulate this function to give us anything other than an undefined function. So this is a non-removable discontinuity, but it's also an infinite. So it is possible to be more than one type of discontinuity. As you approach 0 from the left, it's infinite. 0 from the left is negative infinity. 0 from the right is positive infinity. All right, any questions on that one? it out a little bit. And it's a little bit better. All right. Okay. So what if we have, let's say we want to look at, say g of x is equal to x squared minus 1 divided by x minus 1. So if we take our, just going to rewrite it, x squared minus 1 divided by x minus 1, we can see that our numerator is the difference of squares. And if you remember your difference of squares, you have a squared minus b squared. That's just a minus b times a plus b, or a plus b times a minus b. It doesn't matter the order. So if we have x squared minus 1, where we could rewrite that as 1 squared, that is just x minus 1 times x plus 1. And if you do the FOIL method on this, you'll see you'll just end up right back at x squared minus 1. Same thing here. If you do the FOIL method, you'll end up right back there. So we can go ahead and rewrite that. Instead of x squared minus 1, we can rewrite that as x minus 1 times x plus 1 divided by x minus 1. Move that parenthesis over just a little bit. There we go. Okay. We see x minus 1 cancels out. Okay. So we know that g of x is just equal to x plus 1. But we still have the condition that x cannot equal 1, because that'll give the denominator 0. So if we were to graph x squared minus 1 divided by x minus 1, is the exact same graph of x plus 1, just 1 is undefined. So if we were to graph this, it would kind of, sort of, somewhat look like this, where it would intersect -1 on the x-axis and +1 on the y-axis. And right where, I'll just put it right here, x is equal to 1, it will be undefined. Okay. Now, if we wanted to find the limit as you approach 1 from the left or right, we could just rewrite it as the limit. Oh, bring that up a little bit. As x approaches 1, x squared minus 1 over x minus 1. Where if we did everything we did up here, that just becomes the limit as x approaches 1 of x plus 1. Because if we plug it in here, we get numerator and denominator of 0. But if we do it here, we get the exact same limit, but we still know that x cannot equal 1. So if you use direct substitution, since you couldn't use it at the very beginning, that gives us 1 plus 1, which is just 2. And make that parenthesis a little clearer. There we go. So we know right here, that value where it's undefined, that's a 2. You know, from the left, it's going to equal 2, and from the right, the limit is 2. Okay, so we know that g of x equals x squared minus 1 over x minus 1 is a removable discontinuity. Okay, still not continuous, but you can temporarily remove it to find the limit. All right, any questions on that one? All right, anyone still writing? All right. So now we're going to look at some properties of continuity. Okay, so we kind of looked at discontinuity, so let's look at the properties of continuity. Okay, so first, we're going to let B represent any real number. Okay, so let's assume we have two functions, f of x and g of x. And we know that those two functions are continuous at some value x equals c. So if that's the case, then the following are also continuous. Oops. There we go. That a little neater. There we go. First is the scalar multiple of a function. Which is just multiplying some real number times your function. Okay, so if you get your continuous function and you multiply it by any real number, it's still going to be continuous. So just to visualize it, let's say that we know that f of x equals sine of x is continuous. We know that because if we look at the graph of sine of x, kind of just keeps on going like this over and over. There are no undefined values. There are no breaks anywhere. It's just one long sine wave. So we know it's continuous. So since sine of x is continuous, a little extra dot there, then so is, say, h of x equals 8 times sine of x. Okay, so all the amplitude of 8 is going to do is stretch it vertically, but it will still be continuous. So multiplying a real number times a continuous function means it's still going to be continuous. All right. Any questions on that one? Okay, the next property of continuity is the sum and difference. Okay. So if we add two continuous functions together, their sum or their difference will also be a continuous function. Adding or subtracting them won't change it. So f of x plus or minus g of x is also continuous. So for example, we know that f of x equals x and g of x equals sine of x are both continuous. Okay, and they're continuous everywhere. That's why I didn't put an interval. You can put negative infinity to positive infinity for the interval. Okay. So since they're both continuous, we know that we f of x plus g of x, which is just x plus sine of x, or minus, doesn't matter which one. We'll say plus or minus, is also continuous. So adding them together won't magically make them not continuous anymore. Or subtracting them. I'll finish up on the next page. All right, anyone still writing? All right. Okay, now the product of two continuous functions. So if you have function f of x and multiply it by function g of x, that is also continuous. Okay, so for example, again, we know that f of x equals sine of x, and g of x equals cosine of x are both continuous. Okay. If you graph them, again, no openings, no breaks anywhere, just one long graph for any interval. Okay, so since they're both continuous, if we multiply them together, it's just sine of x times cosine of x is also continuous. Okay, so you can add two continuous functions and still continuous. You can subtract two continuous functions, still continuous. You can multiply them by a real number, still continuous. The only thing you can't guarantee will be continuous is division. Because dividing continuous functions are not guaranteed to be continuous. a continuous quotient. All right, so for example, again, we know that we let f of x equals x and g of x equals sine of x. But we know if we take, I'll say g of x divided by f of x. Even though we'll do the same for f of x divided by g of x. It would be sine of x divided by x is not continuous at x equals 0. Oops. Okay, can I separate this? I'll put another example of this one. So if you have f of x is equal to sine of x, and g of x is equal to cosine of x. If we decide to divide f of x divided by g of x, and that gives us sine of x divided by cosine of x. Which means, since you have two continuous functions, if you divide them in this case, we know that cosine of x cannot equal 0. Which means this would be undefined at every value of x that would make cosine of x equal 0. So this x is equal to, or x cannot equal, pi over 2, positive or negative, 3 pi over 2, 5 pi over 2, and etc. All those values would make you have a denominator of 0. So that denominator of 0 would put a break in your graph. All right, any questions on that one? All right, anyone still writing? All right. So what if we wanted to determine if our function f is discontinuous for any real number? Let's say if we know that f of x is equal to x plus 1 when x is less than 2. It's equal to 3 when x is between 2 and 4. So x is less than or equal, well, 2 is less than or equal to x. X is less than 4. And it's equal to x squared minus 11 when 4 is less than or equal to x. Remember, this is just the same as saying x is greater than or equal to 4. Sometimes they'll switch it up. You can always flip it around as long as your inequality is pointing at the same value. So if it's pointing at the 4 here, you can flip it around and make sure it's pointing at the 4 there. Or you can plug in a numerical value. 4 is less than or equal to 5, so 5 is greater than or equal to 4. Okay. So the first thing I always do is just kind of put it in order. Arrange everything on a number line. Okay. So the first thing you want to do is you want to find your boundary points. And your boundary points all revolve around your constraints. These represent where your boundary points will be located. Okay, so we have x is less than 2. We have x is between 2 and 4. So 2 is less than or equal to x. It's less than 4. And x is greater than 4, you can say 4 is less than x. Less than or equal to x. And again, you don't have to write it out like this. This is just kind of a visual aid. Once you get comfortable, you'll just be able to look at it and tell. So here you can see that your constraints kind of skip at 2 and also skips at 4. So your boundary points are 2 and 4. Like I said, you'll be able to look at this visually and tell. You don't have to do this every time. Two and 4. So we're just going to get those points and mark them on our number line. Remember, that number line goes from negative infinity to positive infinity. So remember, when x is less than 2, actually, let me kind of separate this a little bit, just so I can finish writing. So x is less than 2. That's just the interval from negative infinity to 2. And 2 is going to have a parenthesis next to it, only because you have the less than and not the less than or equal to. And we know when x is less than 2, your f of x is equal to x plus 1. Now the interval between 2 and 4, 2 is less than or equal to x. It's less than 4. Yeah, that looks a lot like a z. Let me replace that. There we go. Well, that's the interval from 2 to 4, but it can include 2 since it's less than or equal to. So we put a bracket for the 2 and a parenthesis for the 4. We know when the intervals from 2 to 4, your f of x is equal to 3. So we know for that interval, f of x is equal to 3. And when 4 is less than or equal to x, or x is greater than 4, 4 is less than or equal to x, we know that represents the interval from 4 to infinity. And 4 gets the bracket because it's the less than or equal to. Or if you flip it, greater than or equal to. So we know when x is greater than or equal to 4, our f of x is equal to x squared minus 11. Okay, now your second step is you're going to look at each one for your conditions of continuity. If each satisfies the conditions of continuity. Clean that F up a little bit. Okay, so first we're going to look at 2. Bring it up a little bit. Okay, so if we look at the first condition, is f of 2 defined? Well, we look at f of 2 from the left and f of 2 from the right. Yeah, f of 2 is equal to 2 plus 1. We're approaching it from the left. which is equal to 3. F of 2, if you approach it from the right, is just equal to 3. So no matter what value of x you put in there, your y is still going to be equal to 3. So we can see here that yes, it is defined. And actually with this one, you solved number 2, or the second condition, already. You want to know, does the limit of f of x at x equals 2 exist? Shortcut to this is, if these two are equal, then you know the limit exists. And the reason why is because if you take the limit as you approach 2 from the left, then that's the limit of x plus 1 as x approaches 2 from the left. Where if we do our direct substitution, that's just 2 plus 1, which is 3, which is what we already did up here. Same thing if you take the limit as x approaches 2 from the right. Well, from the right, that function, f of x, is 3. So the limit of 3 as you approach 2 from the right, well, the limit of a constant is always going to be that constant. So that's just 3. So if the limit is the same from the left and from the right, then we know the limit of f of x as x approaches 2 exists. And it equals 3. Now, the third condition, move that up a little bit. We should have enough room to write third condition. That we want to see if the limit of f of x as x approaches c is equal to f of c. Okay. Well, we can see that from the left, the limit as x approaches 2 from the left of that f of x, which is x plus 1, is equal to 2 plus 1, which is 3. So that's equal to f of 2, because if you plug it in, you just get 3. And again, you already know that up here. The limit of f of x from the right, which is just 3, as x approaches 2 from the right, is again just f of 2, which is 3. So that first step kind of answers a lot for you already. Okay, so all 3 conditions are met, so we know it's continuous at 2. X equals 2. And we'll continue on the next page. All right. Any questions on that one so far? Okay, so we do the exact same thing for our other boundary point, which is 4. And I'm just going to redraw this on the next page so we're not flipping back and forth. Infinity, 2, 4. And you don't have to redraw it if you don't like to. I just wanted to have it all on one page. 2 less than or equal to x less than 4. And we have 4 is less than x. That gives us from 4 to infinity. So this is f of x is equal to x plus 1. F of x is equal to 3. F of x is equal to x squared minus 11. There we go. Okay, so this time we're concentrating on 4. Okay, so we do the same thing at x is equal to 4. Okay, but if we look at the first condition, we want to see if f of 3 is defined. I mean, f of 4 is defined. Okay, but we know that from the left, f of x is equal to 3. So replace x with 4, f of 4 is still equal to 3. Now from the right, f of x is equal to x squared minus 11. Which means that f of 4 is equal to 4 squared minus 11. Four squared is 16. 16 minus 11 is 5. That tells us a lot. Because honestly, once you do this, you don't even have to go anymore. Because we automatically know the limit's not going to exist. So these are both defined. So it actually passes the first condition. Because if you plug in the value 4, you get a real number answer. So they're both defined. But it's going to fail that second condition. Because if we take the limit of f of x as x approaches 4 from the left, and we get that limit of f of x as x approaches 4 from the right, we know they're not going to be equal because we're just going to use direct substitution. Okay, So we have the limit, and you're approaching 4 from the left, your f of x is just 3. So the limit of 3 as x approaches 4 from the left. As you're approaching 4 from the right, your f of x is x squared minus 11. So we use direct substitution, which we already did up here. You know, this side is just going to be 3. This side is going to be 5, which is not true. So it failed the second condition. So we know it's discontinuous at x equals 4. All right, any questions on that one? Oh, I'll leave it up for a few more seconds. All right. So what if we had an example where we wanted to determine the value, clean that E up a little bit, of K. That makes the piecewise function continuous. So let's say if we have f of x is equal to negative 2x plus 5 when x is less than or equal to 3, and k plus 3x when x is greater than 3. Okay. So again, first thing I always do, I draw the number line out. Like I said, all it does is organize all this information. It's not necessary, but it's very helpful. And we can see here our boundary point is just 3. So we don't have to do all the other writing. Okay. So we have x is less than or equal to 3, which is the interval from negative infinity to 3. And because it's less than or equal to, we know we're going to have a bracket. And x is greater than 3, just means we're going to go from 3 to infinity because it's just the greater than. We know we're going to have the parentheses. Okay, so we know that for this interval, our f of x is equal to negative 2x plus 5. And for this interval, we know that f of x is equal to k plus 3x. Now, this is more of a question to see if you understand the concepts of continuity. And it all revolves around knowing the conditions. So to be continuous, the first one is that f of 3 in this case, f of 3 must be defined. The second condition, the limit has to exist. So the limit of f of x approaches 3 from the left, has to equal the limit of f of x as x approaches 3 from the right. And we know the limit of f of x as x approaches 3 has to equal f of 3. Okay, so if we look at the first condition, f of 3 must be defined. So we plug in the value of 3 to the function on the left and to the right of it. So we know that f of 3, I'll put the f of x first. F of x is equal to negative 2x plus 5, which means that f of 3 equals negative 2 times 3 plus 5. Clean that 3 up a little. There we go. Which is equal to negative 1. And the f of x on the right is equal to k plus 3x. Which means that f of 3, we still don't know what k is, so we have to leave it as just k. Plus, now the x we're going to replace with 3. So that's 3 times 3. So that gives us k plus 9. Okay. Now, honestly, you could skip the second step, and I'm going to go through it anyway, but technically you can skip it. Once you do this, you kind of have your answer already. Okay. So we know that the limit must exist. So the limit of f of x, which is negative 2x plus 5, f of x as x approaches 3 from the left is equal to the limit of negative 2x plus 5 as x approaches 3 from the left. And you can skip it because you already did it when you plugged in 3. You did your direct substitution. So that's negative 2 times 3 plus 5, which is still negative 1. Which is why I say you can skip it. And the limit of f of x as x approaches 3 from the right is just the limit k plus 3x as x approaches 3 from the right. So if we plug in 3 there, we still get k plus 3 times 3, just k plus 9. So again, like I said, with this one, you can kind of skip it. But I figured I'd show you anyway. Now for the third condition, we know that the limit of f of x as x approaches 3 has to equal f of 3. Okay, well, we have to find the limit of f of x. So that means that the limit of f of x as x approaches 3 from the left has to equal, actually you could add this on to 2, but we'll do it for 3 anyway. X approaches 3 from the right. Oh, bring that up a little bit. There we go. Now, the reason you could skip 2 is because once you get here, all you have to do is set these two equal. So you could really solve this just in step 1, because this just becomes the limit as you approach 3 from the left is negative 1. The limit as you approach 3 from the right is k plus 9. So if you subtract 9 from both sides, we see that k is just equal to negative 10. Okay, so yep, you could have just solved this right from here, but I figured I'd go through the entire process to show you why you can skip it, not just tell you to skip it. Okay, so we know that if we plug in k equals negative 10, we get negative 10 plus 9, which is negative 1, and negative 1 here. Those two are the same, so we know it covers all the conditions. All right, any questions on that one? All right, anyone still writing? All right. Okay, so now we're going to look at continuity of trigonometric functions. So what if we let C represent some value that's in the domain of a specific trig function? C represent a value and the domain. A trigonometric function. Okay. And really all it is a series of direct substitutions, where if you take the limit as x approaches c of sine of x, that's just sine of c. If c is equal to pi, we're just going to replace it with pi. We have the limit as x approaches c of cosine of x. That's just cosine of c. We have the limit as x approaches c tangent of x. That's just tangent of c. We have the limit as x approaches c cosecant of x. That's just cosecant of c. You can probably kind of see the pattern here. The limit as x approaches c of secant of c is equal to secant of x is secant of c. And the limit as x approaches c of cotangent of x equals cotangent of c. So for example, if you wanted to evaluate the limit of sine of x as x approaches pi over 2. Okay, well, that's just the limit. I'm just going to rewrite it. As x approaches pi over 2 is just sine pi over 2, which is 1. All right. Okay, so what if we wanted to evaluate the limit as x approaches 0 of secant of 2x? Now, once again, we just use direct substitution. approaches 0 is just secant of 2 times 0, which is secant of 0. Okay. Now with secant of 0, we know that secant of x is 1 over cosine of x. Make that a little clearer. Here we go. So that means secant of 0 is 1 over cosine of 0. Cosine of 0 is just 1. So we know that secant of 0 is just 1 over 1, or just 1. All right. Any questions on that one? Okay. Let's say if we wanted to evaluate the limit as x approaches 1/2 of cosine inverse the square root of 2x squared minus square root of 2 over 4. So with this one, or any question like this, you just want to remember that if you have the limit as x approaches c of any composite function, say f of g of x, okay, that limit only applies to the same independent variable function, so we could rewrite that as f of the limit as x approaches c of g of x. We kind of did this before. Not kind of, we definitely did this before. So I'll put kind of an example in here, just to kind of show you that we've done it before. So remember, we had the limit as x approaches 27 of the cube root of x. We could use direct substitution if we wanted to, but kind of show you what we're talking about. We rewrote that as the cube root of the limit as x approaches 27 of x. Which still gave us the cube root of 27. Which is equal to 3. So you don't have to write that down as part of the solution. This is more of a give you an idea of how we're going to approach it. So we can take our original, I'm just going to rewrite that. X approaches 1/2 cosine inverse square root of 2x squared minus, oh, I put square root of 4 over 4. That should be square root of 2 over 4. Sorry about that. Square root of 2 over 4. Okay, minus square root of 2 over 4. And we can rewrite it by just applying the limit to the composite function with the same independent variable. So we can rewrite that as the cosine inverse of the limit of square root of 2x squared minus square root of 2 over 4 as x approaches 1/2. So we can just go ahead and use direct substitution. For this part, we're going to use direct substitution. Because we know if we plug in 1/2, you won't get some undefined value. And we'll just do that right over here on the side. The limit of square root of 2 x squared minus square root of 2 over 4. X approaches 1/2. Well, if we go ahead and use direct substitution, that's just the square root of 2 times 1/2 squared minus square root of 2 over 4. Well, 1/2 squared is just 1/2 times 1/2. So 1/2 times 1/2 is 1/4. So we have square root of 2 times 1/4 minus square root of 2 over 4. Okay. Well, square root of 2 times 1 over 4 is really just square root of 2 over 4 minus square root of 2 over 4, which is equal to 0. So everything in here, we can just replace it with 0. That's all it ends up equaling. So that gives us cosine inverse of 0. Okay, so now we have to solve for cosine inverse of 0. Okay. So to do that, we're going to let it equal something. So we're just going to rewrite it, and we're going to let cosine inverse of 0 equal y. Okay. Now, once we have it set up like that, all we have to do is apply the inverse of cosine inverse, which is cosine. So we're going to apply cosine to both sides of the equal sign, of course. So that gives us cosine of cosine inverse of 0 is equal to cosine of y. And since the cosine function and the cosine inverse functions are inverses of each other, we know that their composition cancels each other out. So we have cosine of y is equal to 0. Okay. Now there are a ton of values of y, actually an infinite number of values of y that will make cosine of y equals 0. But remember, for trig functions, well, with inverse trig functions, we're only worried about what's in the domain of that trig function. And we know that the domain of cosine of y is from 0 to pi. So between 0 and pi, the only value that would make cosine of y equals 0 is pi over 2. Otherwise, we'd be going on forever. Pi over 2, 3 pi over 2, 5 pi over 2, on and on forever. The only value of y in the domain of cosine inverse that makes this true is y is equal to pi over 2. And we know that that y is, here it is, cosine inverse of 0 is equal to that y. So that tells us that the limit as x approaches 1/2 of cosine inverse of square root of 2 times x squared minus square root of 2 over 4 is equal to pi over 2. Okay. So if you run across a problem like this, you might want to go back and look at your either pre-calc or trig textbook to find your domains of your trig functions if you don't know them. But they're really easy to forget if you're not looking at them all the time. All right. Any questions on that one? All right. I'll let everyone finish up. Okay, anyone still writing? All right. Okay. Next, we're going to look at the intermediate value theorem. Here we go. Add them in the wrong pile. All right. So for the intermediate value theorem, let's look at a graph, your x and y axis. Make sure I didn't put anything else in the wrong pile of papers. I did. Keep hitting that disk drive. All right, so let's say if you have a function, and we'll just put function, any random function. And this is our function f of x. Okay, so we know that, just looking at it, that f of x is a continuous and closed function. On the interval from a to b. From x equals a to x equals b. Let's say if this is our value a. We know if we plug a into our function, we get the value f of a. Plug in 3, you get f of 3, 7, you get f of 7, so forth and so on. And for our b, if you plug that in on the graph, you'll get the value f of b. So what if we know that between f of a and f of b, we let some number that we will call k. And k represents any real number between f of a and f of b. So if we pick anywhere between a and b, and we'll say, okay, this is our value k. So we'll say that f of n is equal to k. So if we have k, we see that k lines up with this point on the graph, give or take. That means your n would be probably right there. So if you plug in n, you get f of n, which is equal to some value we'll call k. Okay. So what this shows us is that Nope, not if. Then we know that there is one number, or at least one number, because it could be well, no, if it's a function, then it won't be more than one number. Okay, so there exists a number n, and there exists a number n in our interval from a to b. Where f of n is equal to k. Now, the key to this being true is the fact that it's continuous. Because if the function were not continuous, if you have your x and y axis, so let's say your f of a is this side of the function, and f of b is this side of the function of n. Just put the dot on the wrong end. There we go. Actually, the b, let me shorten that up so it actually fit on the graph. There we go. Okay. And these could be open or closed circles, doesn't matter. The only thing that matters is we know that at n, it could still exist but if it's not in that interval, if it's not already put in that it exists, or if this is a closed circle here, then we already know it exists for n here. Okay, so it has to be continuous. So that means that for some value k in here, there's no solution. Okay, so it does have to be continuous. This is only if f of x is not continuous. The theorem does not work. Right? Anyone still writing? All right. Okay, so let's say, for example, if we want to use the intermediate value theorem, and just for shortcut reasons, the intermediate value theorem, you'll sometimes see IVT. And then we have an extreme value theorem where you'll see EVT, so you'll see those shortcuts. Use the extreme value theorem to show that the polynomial f of x is equal to x to the third power plus 2x minus 1 has a 0 in the interval from 0 to 1. Okay. Well, the first thing we notice is that f of x is continuous. So we see that f of x is continuous on the interval from 0 to 1. Because we know we can plug in any number between 0 and 1 and we'll get a real number answer. It won't be undefined anywhere. So that means we can use it. Now, sometimes they'll throw one at you and it'll be, instead of x to the third power, you might get f of x equals x to the negative 2 power from the interval from -1 to +1. Well, you know it's undefined if it's at x equals 0, so it would stop it right there. You wouldn't be able to use it. Okay, but with this one, it is continuous, so you can use it. Okay, so the first thing we're going to do is we're going to plug in our first and last term, so the two endpoints. So f of 0 is just equal to 0 to the third power plus 2 times 0 minus 1. Well, 0 to the third and 2 times 0, both 0. So we know that f of 0 is equal to -1. And f of 1 is equal to 1 to the third power plus 2 times 1 minus 1. Okay, 1 to the third power is 1, so we have 1 plus 2 minus 1 is just 2. So 3 minus 1. So f of 1 is equal to 2. Okay, so that means, just to kind of help visualize, that f of 0, make our x and y, is equal to -1. And f of 1 is equal to 2. And put our 1 right here. So f of 1 is equal to 2. So as long as it's continuous, we know that at some point, this graph is going to have to cross the x-axis to get to the continuation of it. So the only way it can do that is knowing that at some value c, it has to cross that x-axis. Okay. So that's how we know, because of the intermediate value theorem, it's continuous, and we know that if it's continuous, at some point, there's going to be a value where f of c would have to equal 0. So by the intermediate value theorem, there exists some point where f of c equals 0 in the interval from x equals 0 to x equals 1. it all revolves around the fact that one endpoint is negative and one endpoint is positive. Since f of 0, let's clean that up a little bit, is negative, and f of 1 is positive. Now, if they were both positive, so let's say f of 0 was equal to positive 1. So if they're both positive, we have no guarantees that this function is going to drop back down to cross the x-axis and go back up. It could go right there straight to it. So just the fact of the intermediate value theorem does say yes, it eventually has to cross that to get to 0. I mean, to get to 2. So it does have to equal 0 at some point. All right, any questions on that one? All right, so we will go ahead and stop there, and we will pick up, well, actually, we're done on this section, so we will start chapter 3. This chapter is only 4 sections.